Welcome back to the deep dive, where we take a stack of dense, fascinating source material and card out the aha moments you need to feel instantly well-informed.
And today, we are wading into territory that is...
Well, that's absolutely mind-bending.
It really is. We receive sources that combine geometry, ancient philosophy, modular arithmetic, and a simple Python script, all centered around just a dazzling visual pattern.
That's right. At its heart, this entire deep dive is triggered by a user-generated computer program. This script performs one deceptively simple mathematical task.
Okay, what is it?
It multiplies coordinates on a massive grid and then calculates the digital root of the product. And the complexity just explodes from that simple command.
Okay, let's unpack this immediately, because on the surface, calculating a product's digital root sounds like, basic grade school math. But the visual output, especially for base 10, is this massive symmetrical 27 by 27 grid of digits that our source material has provocatively dubbed the fractal of ceneeze. And that's our mission. It's to understand why the grid looks the way it does. We are diving deep into what this geometric structure actually represents mathematically.
To show that it's not a coincidence.
Exactly. To show that its patterns and its symmetries are not coincidental, but inevitable outcomes of modular arithmetic. And then we also need to analyze how those predictable patterns intersect with these profound historical and philosophical ideas.
Particularly the endlessly repeating sequence of 369.
That's the one.
We're working with a fascinating mix of evidence here. We have the raw Python function itself. We have the huge, compelling visual output for base 10, and then these unique foundational tiles that show us the pattern in bases 2 through 9.
It's like having the full set of blueprints, the finished skyscraper, and all the scaled-down models. It's a complete package.
So to really understand the grand claims the user is making, we have to start with the fundamental mathematics that govern this entire structure.
Precisely. We need to understand the underlying mathematical recipe first to truly appreciate why the finished product, this fractal of ceneezer, looks so organized, so repetitive, and so symmetrical.
Okay, let's start with the atomic unit of this entire operation, the digital root. For those of us who have long forgotten this concept, maybe only remembering it from a brief detour in elementary school, how do we define it simply?
It's a concept of numerical reduction. So you take any number, say 7,894.
Okay.
You just sum its digits. So 7 plus 8 plus 9 plus 4, that equals 28.
Right, still 2 digits.
So you repeat the process.
Yeah.
2 plus 8 equals 10, still 2 digits. 1 plus 0 equals 1. That final single digit 1 is the digital root of 7,894.
So it's the ultimate reduction of a number to its single-digit essence. But here's where the analysis gets powerful and what makes the grid generation so predictable. The digital root isn't just some quirky arithmetic trick.
No, not at all.
It is mathematically identical to a much more fundamental concept, which is modular arithmetic. And this is the aha moment that unlocks the whole deep dive.
That is the absolute key. For any non-zero number n in a given base b, the digital root of n is mathematically equivalent to n modulo b minus 1.
Right.
So in our central example, the base 10 grid, since b is 10, b minus 1 is 9. So the digital root of any number is essentially just that number, modulo 9.
Okay, wait, I want to linger on that for a second because it sounds so abstract. If the digital root is just n mod 9, why bother with the whole tedious process of summing digits over and over?
Well, because the summation process is just a highly accessible and ancient method of performing that exact modulo operation. It's a shortcut.
How so?
When you sum the digits, you are essentially subtracting multiples of 9 until you reach the remainder. Think about the number 10.
Okay, 10 mod 9 is 1.
Right, and the digital root is 1 plus 0, also 1. Think about 99. 99 mod 9 is 0. The digital root is 9 plus 9, which is 18. 1 plus 8 is 9. This mathematical equivalence is what guarantees the pattern's repetition.
So that means the massive 27 by 27 grid isn't just a random scattering of numbers.
Not at all.
It's a visual, geometric map of multiplication results, but specifically in terms of their remainder when divided by 9.
That's it.
So if the product of two coordinates, I times j, is, say, 158, its digital root is 1 plus 5 plus 8, 14. Then 1 plus 4 is 5.
And 158 divided by 9 leaves a remainder of
5.
5. Correct. This underlying law, this periodicity based on the modulus, is what creates the astonishing symmetry.
Yeah.
Every time the product increases by 9, the digital root just cycles back to the next number in the sequence. This repeating cycle is what the user is visualizing.
Now let's look at the Python code itself. The core calculation is the digital root of the absolute value of the product of the coordinates. So digital root of the absolute value of I times j and base b.
Yes.
But the sources emphasize that the code includes two crucial adjustments. These handle edge cases and make sure the final output matches the culturally understood definition of the digital root.
And these adjustments are critical, particularly the second one, because standard mathematical modular arithmetic doesn't always map perfectly onto the human concept of the digital root.
The first rule is straightforward. If the product I times j equals 0, the root is 0. That covers all the rows and columns that are indexed by 0.
That's the easy part. The second adjustment, though, that handles the definition of digital root for multiples of b minus 1.
Which is 9 in base 10.
Right. In standard arithmetic, if a number is a perfect multiple of the modulus, the result of the modulo operation is 0. So 81 mod 9 is 0.
But the digital root of 81 is 8 plus 1. It's 9.
Exactly. So the source code needs to specifically override that standard mathematical 0 result. The rule states, if the product is non-zero and the modulo b minus 1 result is 0, then the digital root must be set to b minus 1.
So for any non-zero multiple of 9, the code forces the output to be 9, not 0.
It has to.
And this is why the base 10 grid is filled with all those 9s in strategic places, giving the grid its characteristic dark bands. This rule ensures the output range is 0 to 9, which is required for a complete visualization.
Without that override, the structure would look fundamentally different, much less rich.
Okay, let's zoom out from the single calculation to the architecture of the grid. The source material talks about a base unit or a tile. How is this tile mathematically defined?
For any base b, the fundamental, non-redundant mathematical pattern is captured entirely within the b minus 1 by b minus 1 tile.
And that's generated by non-zero indices.
Right. This runs from index I equals 1 to b minus 1 and j equals 1 to b minus 1.
Yeah.
So for base 10, the fundamental tile is 9 by 9, covering products from 1 times 1 up to 9 times 9. This is the mathematical core of the entire structure.
And then the Python script takes this single 9 by 9 pattern and uses it to build that massive 27 by 27 grid. How does the indexing achieve that?
The full grid is always 3 times b minus 1 by 3 times b minus 1.
So in base 10, that's 27 by 27.
Yes. The script generates this by setting the index range from negative b minus 1 up to 2 times b minus 1 minus 1. So for base 10, this means indices from negative 9 up to 17.
That gives us 27 indices total. And the inclusion of negative numbers and that big range, that's the key to the tiling.
It is, because the digital root of a number n is the same as the digital root of n plus 9 times k. The pattern exhibits perfect periodicity every 9 steps. By spanning 27 indices, we're ensuring the grid is composed of a 3 by 3 tiling of that base unit.
The patterns just repeat 3 times horizontally and 3 times vertically.
And the negative indices simply flip and reflect the pattern across the 0 axis, which maintains that beautiful symmetry.
That makes the geometry crystal clear. The structure isn't just fractal in a visual sense, but in the mathematical sense of self-similarity across scales, dictated purely by the laws of modularity. Now, this periodicity also explains the rapid increase in complexity as the base increases.
Absolutely. The tile size, b minus 1, increases linearly. So base 3 has a tiny 2 by 2 tile, whereas base 9 has an 8 by 8 tile. But the internal complexity just explodes because the number of possible remainders increases.
And crucially, the properties of the modulus b minus 1 change dramatically.
Yes.
Can you elaborate on that? What difference does it make if b minus 1 is a prime number versus a composite one?
Oh, it makes all the difference in the world. If b minus 1 is prime, say you're in base 6, so the modulus is 5, the arithmetic is very neat. Every non-zero number is a generator, meaning if you multiply by all the other numbers, it cycles through all the residues in a predictable, non-repeating sequence within the tile.
But if b minus 1 is composite, like 6 for base 7 or 8 for base 9 or 9 for base 10,
then you have factors, we call them zero divisors, that create high internal repetition and these specific bands of digits.
Wait, let's pause and define that term for the listener. What is a zero divisor in this context?
A zero divisor, when you're working with a modulus m, is a non-zero number a, such that when you multiply it by another non-zero number b, the product a times b is a multiple of m.
So basically, a times b is the same as 0 in that modulo system.
Exactly. So in base 7, our modulus is 6. Numbers like 2 and 3 are zero divisors, because 2 times 3 is 6, and 6 is congruent to 0 mod 6.
So when you multiply by those numbers in the grid, they force high repetition.
Tremendous repetition. We'll see that in a bit.
So the core takeaway from this foundational mathematical section is that the pattern is structurally required. It's an unavoidable truth of arithmetic, visualized. And that visualization is what the user called the fractal of ceneeze. Why that name?
The user refers to it as a fractal because of the self-similarity. The 27 by 27 grid is built from smaller 9 by 9 copies. The term ceneeze, well, that appears to be entirely unique to this source material.
A personal name, perhaps?
Perhaps a personal name or a specific numerological reference. But in the mathematical sense, the fractal property is really just that self-tiling nature driven by periodicity.
Now we have the tools to analyze the actual image, the 27 by 27 base 10 grid. And the first, most visually shocking pattern that the user specifically highlighted as a unique discovery was the cross of zeros.
When you look at the full output, row 9 and column 9 are entirely filled with the digit 0. This creates a perfect, bold axis right through the center of the structure.
Yes.
It's undeniably striking.
And the user claimed this was an unreported feature, suggesting some special significance or genius in its discovery.
Right.
But if we go back to our math from section 1, we realize this is the ultimate example of a pattern that is completely unavoidable.
It is absolutely mathematical necessity, and that distinction is paramount. As we established, the indices run from negative b-1 up to 2 times b-1 minus 1. In base 10, that's negative 9 to 17.
And the coordinate index I equals 0 is precisely the 10th index in that sequence. That's row 9. And the coordinate j equals 0 is column 9.
Yes. So if the row index I is 0, the product I times j is always 0, regardless of what j is.
And our code explicitly states that the digital root of 0 is 0?
So row 9 must be zeros, and column 9 must be zeros. The cross of zeros isn't some ingenious feature discovered by the user. It's an inherent mathematically required axis that results from including the index 0 in the coordinate range. It's what organizes the whole thing.
Wait, doesn't that undermine the user's philosophical claims immediately? If their big, unreported feature is just a standard result of including 0 in the index set.
That's the critical point for our analysis.
Then their entire discovery is based on visualizing an inevitability, not some profound hidden truth.
The mathematical reality stands separate from the human perception. The cross of zeros is a genuine visual phenomenon, yes.
Right.
But its existence tells us more about the definition of multiplication than it does about hidden cosmic secrets.
So it changes the focus.
It changes the focus from what is the spiritual meaning of the cross to why did the person who coded the script choose to center the visualization on the 0 point?
And the answer to that second question is simple, because that's where the structure naturally stabilizes. The entire pattern radiates outward from that required 0 axis.
To appreciate this further, we should briefly look at the unique fingerprints generated by the base tiles of, say, bases 2 through 9. Each b-1 by b-1 tile tells a unique story about the arithmetic of that specific base.
We noted earlier that 2 properties hold true for all bases: symmetry and the edge patterns. Let's revisit the symmetry first.
The tile is perfectly symmetric across the main diagonal. This is simply the visualization of the commutative property of multiplication.
Right. A times b is the same as b times a.
So the digital root of a times b equals the digital root of b times a. The grid is a perfect mirror image of itself.
Then we have the edge patterns. The first row and column corresponding to I equals 1 are trivially easy, 1, 2, 3, all the way up to b-1.
Because multiplying by 1 changes nothing. But the last row and column are far more powerful because they demonstrate that crucial rule we discussed.
The special handling of multiples of b-1.
Yes. In base 10, the last row, index I equals 9, is entirely filled with 9s.
Why is that universally true for all bases?
Because the last index is always b-1. So any product, I times b-1, is automatically a multiple of b-1. And by that custom rule in the code, the digital root of any non-zero multiple of b-1 is b-1 itself.
So base 4 ends in 3s, base 6 ends in 5s.
You can instantly identify the base just by looking at the edge of its true base tile. It's a dead giveaway.
Now let's talk about that internal complexity using those 0 divisors we defined. Let's look at base 5 versus base 7 as examples from our sources.
Okay, base 5 has a modulus of b-1, which is 4. Since 4 isn't prime, it has a 0 divisor, which is 2. So its 4x4 tile is highly structured, but not overwhelmingly complex.
What does the row for 2 look like?
If you look at the I equals 2 row, it cycles. Digital root of 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 3, and 2 times 4 is 4. It creates a highly compressed pattern.
Now compare that to base 7. The modulus there is 6.
6 is a highly composite number. Its zero divisors are 2, 3, and 4. And this is where the patterns become extremely restrictive. Look at row 3 in the 6 by 6 base 7 tile.
What do you see?
It's just 3, 6, 3, 6, 3, 6. If you multiply by 3 in modulo 6 arithmetic, you can only get 3 or 6 as a result. That's it.
And that structural restriction is due to the shared factors between the index 3 and the modulus 6.
Absolutely. The structural analysis shows that every base has a unique, mathematically dictated fingerprint based on the properties of b-1 and its divisors. The complexity is inherent in the number-based system itself.
And this brings us back to base 10 and the star of the show, the 3, 6, 9 sequence, which just dominates the visual grid. We've established that 3, 6, and 9 are special because they are the factors of the modulus 9.
They are the essential structural elements of base 10 digital root arithmetic. Because they are the only divisors of 9, besides 1 and 9 itself, multiplying by 3 or 6 fundamentally restricts the resulting digital roots to that specific set.
Let's visualize this on the 27 by 27 grid. We see these thick, dark bands corresponding to rows and columns that are multiples of 3, but not 9. The visual evidence it's just stunning.
Take row 3, as seen in the source material. If you ignore the central 0 column, the digits are just cyclically repeating, 936, 936, 936, and so on. Even within the full 27 by 27 structure, which includes indices from -9 to 17, this repetition is flawless because of that 9-step periodicity.
Okay, so why does multiplying by 3 cycle so predictably through the set of 3, 6, and 9 modulo 9?
Let's just trace it. When you multiply by 3, you're mapping the whole set of 9 residues onto a smaller, highly structured subset. So
3 times 1 is 3.
3 times 6 is 6. 3 times 3 is 9. The digital root is 9.
3 times 4 is 12. Digital root is 3.
3 times 5 is 15. Digital root is 6.
3 times 6 is 18. Digital root is 9.
And it just keeps going like that. 3, 6, 9, 3, 6, 9. It's a closed 3-step loop. The system is entirely contained within 3, 6, and 9.
And this structural requirement explains the visual geometry. The 3, 6, 9 bands are not random lines of light and shadow. They are the geometrically precise manifestation of the multiplication table of 3 and 6 within the modulo 9 system. The mathematical discovery is clear. The geometry of the base 10 digital root grid is dictated by the factors of 9. And this provides the crucial, rigid bridge to the next part of our deep dive, where the user takes this concrete mathematical pattern and makes a profound philosophical leap.
Yes, the math is undeniable. But when the user saw this repeating 369 sequence, a sequence already deeply ingrained in human culture, they clearly felt they were looking at something sacred.
An underlying code.
An underlying code. The question then becomes, how does one make that leap from necessary arithmetic to cosmic design?
Before we leave the math, though, we need to clarify one subtle but crucial detail that impacts the user's final provocative thought.
Oh, yes.
We've been discussing the 27 by 27 grid and the 9 by 9 base tile. Can you clearly differentiate the 9 by 9 central block of the output from the true 9 by 9 base tile?
This is vital for understanding the conclusion. The full output spans indices from 9 to 9 to 17. The central 9 by 9 block, the one that contains a cross of zeros, spans indices 0 through 8.
Okay, so if you're looking directly at the cross and the pattern right around it in the visual center, you are looking at products involving the numbers 0 through 8.
Exactly. But the true base tile, the one that contains the complete, non-redundant multiplicative pattern of base 10, is defined by indices 1 through 9.
Not 0 through 8.
No, 1 through 9. This true tile is required to show the full cycle of 9 non-zero residues.
Which means the true tile, the one that defines the entire system, includes that row and column of all 9s, the one for index 9.
Right.
And that crucial edge pattern is not contained in the 0 to 8 central block.
No, it is not. The true 9 by 9 pattern is slightly offset from the central, visually prominent 9 by 9 block defined by the 0 axis. The mathematical nature of the base 10 pattern actually lies just outside the visual center that the code provides. The subtle offset is extremely significant when we return to it later.
Okay, so having established the mathematical necessity of the 369 sequence in base 10, we must now address the user's interpretation. The source material ties these patterns directly to profound philosophical and spiritual meaning, specifically noting a connection to Nikola Tesla and, most dramatically, the biblical narrative.
And our duty as guides in this deep dive is to impartially report and contextualize the claims made in the source material. We have to acknowledge the powerful, profound personal interpretation the user applies.
Claiming this observation as proof I've met Jesus.
Yes. While we analyze the historical and theological foundation of their argument, The commonality of 3, 6, and 9 in these disparate fields is undeniably the catalyst for this whole synthesis.
Let's start with the biblical context. The source material highlights the structure of the crucifixion story, noting that the key events occur at the 3rd, 6th, and 9th hours. This provides a narrative structure defined entirely by that sequence.
To understand the timing, we must reiterate the use of ancient Jewish timekeeping. The day was measured from sunrise, which was designated as the first hour, typically around 6:03 a.m. modern time.
And the 12 hours of daylight then progressed in these 3-hour blocks.
Yes.
So let's lay out the precise sequence of events anchored to the 3, 6, 9 markers.
The first key marker is the 3rd hour, corresponding to 9:00 a.m. Mark 15.25 explicitly states that Jesus was crucified at the 3rd hour. This sets the stage for the physical ordeal.
Okay, and then 3 hours later, we reach the midpoint of the day, the 6th hour, or noon.
At the 6th hour, 12:00 p.m., the atmosphere shifts dramatically. The Synoptic Gospels, Matthew, Mark, and Luke all concur that a supernatural darkness fell over the land, lasting until the 9th hour. Matthew 27.45 marks this specific time.
So the structural use of the 6th hour divides the narrative into a distinct period of suffering under this celestial distress.
It does. And the final climactic event occurs at the 9th hour, 3:00 p.m.
The end of the story.
This is the conclusion. Matthew 27.4650 details that Jesus cried out, quoting Psalm 22, and then gave up the spirit. The entire traumatic arc of the crucifixion, from the ascent to the death, is defined and organized by these 3-hour intervals, 3, 6, and 9.
This intentional structure is what the user links to the mathematical structure of base 10, but there is important scholarly nuance here, especially concerning the Gospel of John, which complicates the strict 3-6-9 timeline.
Indeed. John 19.12 places Jesus before Pilate at the 6th hour, which is clearly before the crucifixion itself, and this apparent contradiction has fueled historical theories for centuries.
So what's one of the leading theories to reconcile the timing systems?
One theory posits a difference between the Jewish timekeeping, used by the Synoptic Gospels, counting from 6 a.m., and a potential variant of Roman timekeeping, perhaps a 12-hour civil day starting at midnight, which John might have used.
So if the 6th hour in John meant 6:00 a.m., that would place the events before Pilate appropriately early in the morning.
Correct. But if we dismiss the need for minute-by-minute precision, the meaning changes entirely.
How so?
Well, the simpler explanation is that the references to the 3rd, 6th, and 9th hours were never intended as, GPS coordinates for a specific minute.
Yeah.
They were broad, liturgical 3-hour blocks of time that provided a powerful framework for the narrative. They're structural devices.
So the consistency is less about the inherent mystical quality of 3, 6, and 9.
And more about the human need to organize important events into aesthetically pleasing rhythmic intervals that align with the systems we already use, like base 10 counting.
If the 3-6-9 sequence is structurally required by base 10 math, isn't finding it in base 10 theology just proof that humans universally build their narratives around their counting system, not proof of a grand cosmic code?
That is precisely the distinction. That is the essential skepticism we have to maintain here. We see the influence of our fundamental measurement system, base 10 arithmetic, and 12-hour daylight shaping our narratives. The mathematical inevitability of the digital root grid is mirrored by the narrative inevitability of using those highly divisible numbers for temporal organization.
Whether structural or sacred, the 3-6-9 sequence holds this powerful, almost archetypal place in human thought far beyond a single biblical narrative. Let's explore why these numbers are so pervasive across science, philosophy, and numerology.
They represent a fundamental progression in division. You can start with science and geometry. Our world is defined by 3 spatial dimensions:
Right.
length, width, depth.
Right.
In particle physics, the fundamental components of matter are often organized in sets of 3 or 6. We mentioned the 6 types of quarks earlier.
And then there's the natural geometry that minimizes effort and maximizes density, which often resolves to 6.
The hexagon. The 6-sided structure of beehive cells, basalt columns, snowflakes. A circle can be perfectly divided by 6 radii equal to the radius itself. These aren't random. They're mathematical and energetic realities that govern efficiency in the physical world.
Okay, now we move to the realm of philosophy and numerology, where this sequence becomes mystical, most famously tied to Nikola Tesla.
The modern legend holds that Tesla considered 3, 6, and 9 to be the key to the universe.
And that understanding them would unlock vast cosmic secrets.
Right. This belief is extremely popular today, often associated with concepts like vortex mathematics.
But the sources are careful to distinguish fact from legend here. Tesla certainly had a documented and intense personal obsession with the number 3. It was almost certainly a form of obsessive-compulsive disorder.
Yes, his personal rituals are documented. He would circle the building 3 times. He would only stay in certain hotel rooms or insist on 3 napkins at dinner. But the grand cosmological claims that he tied the 369 sequence explicitly to toroidal geometry and the core energy mechanics of the universe. These claims largely originated later in the speculative realm of numerology.
And they lack solid, verifiable quotes from Tesla himself.
They do. So the pattern is real in his personal life, but the interpretation is speculative, which mirrors our entire deep dive, doesn't it?
It does. The mathematical pattern in the grid is real. The vast interpretation applied to it by the user is speculative.
And finally, we see the pattern woven deeply into global religious thought.
It's everywhere. Christianity has the Holy Trinity, Father, Son, and Holy Spirit. Buddhism relies on the triple gem: the Buddha, the Dharma, and the Sangha.
Hinduism organizes its structure around the Trimurti: Brahma the creator, Vishnu the preserver, and Shiva the destroyer. The recurrence of 3 and its multiples is rooted in the fact that these numbers are foundational.
They're just easy to work with.
They are. They're small, easy to visualize geometrically, and they divide our most common measurement systems. They provide an elegant scaffolding upon which human systems, whether arithmetic or theological, are naturally built.
They're powerful both mathematically and narratively, and that power is why seeing them appear in a simple calculation like the digital root of a product feels so profound. It feels like you're tacking into a universal constant.